So now we're going to get into combustion reactions, and we saw these reactions in experiment 10. I went through and explained how to balance them, and at first it was like, how are you getting this? There's a system. As long as you follow the system, it's a lot easier. And then I also have classified carbon atoms as primary, secondary, or tertiary. I'll teach you the primary, secondary, and tertiary. This we will find useful a little bit later on in the unit, so just stick with me. It's nothing major. So in the example of ethane that I have right here, wait a second, let me move. Let's go from tertiary to primary. So if you have a carbon that is bonded to three other groups or four other groups. I'm very off on this. So you have 1, 2, 3 groups bonded to this carbon. And this one is a hydrogen. You will call this carbon a tertiary. So tertiary carbon. So it's bonded to 3 other non-hydrogens. Sorry that this is so. We go into this for amines too, so I'm getting mixed up. Secondary, you have a carbon that looks like this. So this carbon right here is secondary. And you can see why it's secondary, because it's bonded to 2 other groups that are not hydrogens. I'm going to draw a line through this one. No, and I'm drawing a line through this one. I'm off today. Okay, so CH3OH. You see how this carbon right here is bonded to one other group that's not hydrogen. So that makes it a primary. Now, if you had a carbon like this one that doesn't have any hydrogens on it, you would say that that is quaternary. But our objective just had us go through primary, secondary, and tertiary. But if you wanted to know, what would it be called if there were 4 other groups? And I was shifted off, so that's why. So there might be a question where we ask you whether it's a primary, secondary, or tertiary carbon. And this really helps you with reactions later on. So on Wednesday night, we will probably get more into reactions where recognizing whether they're primary, secondary, or tertiary is extremely helpful. Okay, combustion reactions. This is what we saw in experiment 10. A combustion reaction, we are around these every day, your combustion engine in your car. So this is a chemical reaction that produces a flame due to burning with oxygen. So there are two types of combustion. There's complete and incomplete. I'm going to write out. So with these types of reactions, what you always see is oxygen as a reactant and water as a product. So you will always see that. So if you can't remember anything else but these two things, you know, on a 4-point question, if you could write both of those, oxygen and water, you would get 2 out of 4 points. You totally blank on this, you know, so keep that in mind that these are exactly the same, whether it's complete or incomplete. What differs between complete and incomplete is your product. Complete in combustion is CO2, so carbon dioxide. Incomplete combustion is carbon monoxide. Carbon monoxide, you know, that's what we have incomplete combustion reactions all the time. That's why you don't want to leave your car running in the garage with the garage shut, because you know, the carbon monoxide, you would start breathing that in, that competes for oxygen, and you die. This also happens with your furnace. If your furnace isn't operating properly, you could have carbon monoxide. You know, that is your product. Your combustion's not working properly. So I highly encourage you all, if you don't have a carbon monoxide detector, to get one. You know, we had close family friends, and they almost died because of carbon monoxide poisoning. It just kind of, you know, the wife said, I'm not feeling that well, I kind of feel dizzy, and then the kids started saying that, and then the husband was still with it to recognize that this wasn't right. So they got out of the house, and sure enough, they had very high levels of carbon monoxide. And it was just one of those things. They didn't get their furnace, you know, checked, and they didn't have a carbon monoxide detector. So now they always advocate, you know, whenever they see anybody who doesn't have a carbon monoxide detector, get one. Because if it had happened while they were sleeping, they wouldn't have woken up. So, with both complete and incomplete combustion, you will be given some sort of hydrocarbon. The hydrocarbon, you know, it can be an alkane, it could be an alkene, it could be an alkyne, but it has carbons and hydrogens that react with oxygen. So it's definitely going to be something organic. Now, we could ask you a question exactly like this on a quiz or an exam. Write the balanced chemical equation for the complete combustion of ethane. You know everything to fill this out. But when you get your exam or your quiz and you, oh my gosh, I have no idea what this question is asking, take it step by step. Probably the first thing that is helpful when working with these reactions is to just draw your arrow. You know, start there. And you've done something. You're moving in the right direction. You're getting that answer put down. Pay attention to whether it's complete or incomplete combustion. So, you know, highlight this. What does complete combustion mean? That means I get CO2 and water. And a lot of times students will get the CO2 and the water, but they forget the oxygen. if you forget the oxygen, it's going to be really hard to balance this reaction. So don't forget the oxygen. Now, ethane. Writing the molecular formula of ethane will make this equation easier to balance. If you write out the chemical structure of ethane, it's not going to be that easy to balance. So how many carbons in ethane? C2. And then how many hydrogens? C2H6. So write that, C2H6. So now we went over this when we did experiment 10, but it always bears repeating. What do you balance first? Carbons. Are our carbons balanced right now? How would I balance it? 2 in front of the CO2. Okay. Now that's balanced. What do we balance after the carbons? Hydrogens. Good. So hydrogens. Are our hydrogens balanced right now? How would I balance that? 3 on the right. Good. Lastly, we balance the oxygens. So how would we balance the oxygens? Careful, because they're in both of your products. So it's 2 times 2. So 2 times 2 plus 3. So that's 7. Whenever you have the odd-even problem, that's when you use the fractions. You do not use fractions when you have even-even, because you can just put a coefficient in front of oxygen. So this is when, so you have an odd, use fraction. So the fraction that I'm going to put in front of my oxygen is 7 over 2. Because if you multiply 7 over 2 times 2, that's how you get 7. But we cannot have fractions in our chemical equation. We have to have whole number coefficients. So how do we get rid of this fraction? Multiply everything by 2. So I'm going to multiply this. If you can imagine putting a parentheses around this. So you're multiplying everything here by 2, which you can't see. So now my coefficient in front of ethane is going to be 2. My coefficient in front of oxygen will be what? 7. Yeah. 7. My coefficient in front of CO2 will be 4. My coefficient in front of water will be. So if you're doubting, you know, when you multiply the 2 times the fraction, like, is that right? Double check yourself. Count up your oxygens on this side. 4 times 2, I have 8, plus 6 will give me 14. 7 times 2 gives me 14. So I have a balanced number of oxygens now. Now, can 2, 7, 4, 6, can those be simplified? No. So you're done. So a lot of times students get tripped up by this using fractions, and they think, I have to use fractions for every combustion reaction. You only use it when you have the odd-even problem. So whenever you get an odd number on the right side, that's when you use the fractions. Okay, so I want you to balance each of these reactions and classify them. And when I say classify, either incomplete or complete combustion. Okay, so the first and the last reaction are complete. And then the middle one is incomplete. And the coefficients that you should have for your reactions, the first one, 1, 12, 8, 8. Is that what everybody got? You have 16 plus 8, that's 24 oxygens. 12 times 2 gives you 24. I know, it's easy. Once you get into the double digits of doing math and keeping track of your oxygens, it can get tricky. But, you know, just go back and check yourself a few times, especially if you know that you have a tendency to do your math wrong. It happens. Okay, the second one, coefficients. You get an odd number, so you have to multiply by 2. So 2, 5, 4, and 6. And then the last one is 2, 15, 10, and 10. Now the primary, secondary, tertiary, that I gave a very confusing explanation of in the beginning. Let me give you an example of what you could see, expect of us to ask you. So if I give you a molecule, I gave you this molecule, and I asked you, how many primary carbons are there? So remember, the primary ones are the CH3s. There are 3 primary carbons. So you have.
So basically, like all your carbons are
Mm-hmm. All your terminal ones that have hydrogen, 3 hydrogens on it. And then how many secondary carbons are there? 1. So you just have this one as a secondary. This is your primary. And so you just have 1 secondary. What about your tertiary carbon? 1 tertiary carbon. So that's what you can expect to see the questions that we'll ask of you. You know, it doesn't necessarily have to be a carbon connected to it. It could be like an alcohol, an OH, or something like that. But you're just looking at how many substituents your carbon has on it. So if it just has 1, then it's primary. If it has 2, then it's secondary. If it has 3, then it's tertiary. And quaternary, we don't expect you to know in this class. So, but if you ever come across a molecule that's highly substituted, that's quaternary carbon. Questions on combustion reactions? Okay. All right. So chapter 12, objective 12.1. The objective that we want you to know for this section in your book is to write the IUPAC names for alkenes and alkynes. And this includes cyclo, and write their structures from names. It's like everything we've expected of you for alkanes, but now we're adding alkenes and alkynes in the cyclo. So I think at this point you are getting used to the organic. You know, I might be speaking incorrectly. Hopefully it's a little true, but you know, you're getting used to this way of thinking about things and going, you know, oh, the longest continuous chain of carbons. So now, in this portion of Unit 3, we won't have the A and E ending. We might have the E and E ending for the alkene, or the Y and E ending for the alkyne. When you take the test, everything will be mixed together. You'll have your alkanes, you'll have your alkenes, you'll have your alkynes. But by the time we get to that point, you will be experienced enough to name them all. Yes. Yeah, I know this portion, students are, oh, this is going to be so bad. But really, you have put in a lot of work already to, get to the point where you can name chains and, so. Okay, so an unsaturated hydrocarbon. This is a hydrocarbon with at least one double or triple bond. And remember, a double bond looks like this, a triple bond looks like that. So unsaturated. If that term doesn't immediately evoke a double bond or triple bond in your mind, try to get that term to, okay, that means double or triple bond. But it always took me a while to equate those two. Saturated means that it has all the hydrogens. So if you don't have, so remember, saturated I always like to think of it as it's saturated with hydrogens. That makes sense. Saturated with hydrogens. Where you have CH3, CH3. That's as many hydrogens as you're going to get on those carbons. Whereas here, when you have two carbons and a double bond between them, it's going to be CH2, CH2. So it's unsaturated. Does that make more sense if it's, this has fewer hydrogens. Because of the double bond. And if you imagine a triple bond, then it would just be CH, triple bond, CH. But the way this definition works, anytime you have a hydrocarbon with at least one double bond or one triple bond, it's unsaturated. Now, naming alkenes and alkynes. You go about it the same way that you did for alkenes. You're going to determine the longest continuous carbon chain. The only difference is now your parent has to contain the double or triple bond. So I always think of this, when you become a parent, you gain a lot more responsibility. And if there is a double or triple bond present in a molecule, that parent is responsible for it. Okay? So assign the first carbon atom of the double or triple bond the lowest possible number. It's very similar to what we had before with the methyl and the ethyl and the isopropyl, all that. So name the substituents with position number. Okay, we've done that before. List substituents alphabetically in front of the parent using hyphens and commas where appropriate. Remove the E from the parent and add ene for alkene and add ine for alkyne. Okay, well, kind of makes sense. Let's go through an example. So this molecule I have here, what's the longest continuous chain of carbons that contains the alkene? 5. Okay, so you have 1, 2, 3, 4, 5. So the parent, how many, the parent's last name? Pence. And the ending, so you would think if it didn't have any double bonds, it would be pentane. But because it has a double bond, it's pentene. So pentene. Not Pantene. shampoo and conditioner. Although I probably would be pretty generous.
And is that just the methyl on there, so 2 methyl?
Right. So now, with this parental responsibility, taking over that double bond, you have to tell me where the double bond is. And you're going to list the lowest number on that double bond. So you have two possibilities in this numbering scheme, 1, 2, 3, 4, 5. Within this numbering scheme, there would be 2 pentene. And your methyl would be on the 2. So it would be 2 methyl, 2 pentene. If I number, you always list the lowest number of the double bond. So I wouldn't say 3 pentenes. The other numbering scheme, this would be 3 pentene. But that one, so you list the lowest number.
Or the connection between the two.
So here. But the circle numbering scheme doesn't work out because it makes the substituents higher. It makes the double bond higher. So my name would be 2, I have this methyl, 2 methyl, 2 pentene. So with alkenes and with alkynes, you now have to have a number in front of your parent. Whereas before, if it was just 2 methyl pentane, you wouldn't have to have a number. Now there's such a thing as dienes, where you have 2 double bonds. Dienes exist as well, where you have 2 triple bonds. And for this course, we simplify our organic molecules. There are a lot of molecules out there that exist that have a double bond, a triple bond, a nitro, an SH, all these different functional groups. But in order for you to name them easily, we try to keep them as simple as possible. So on these drug inserts, you see the structures, and you see all these functional groups. And then you look at the IUPAC name, and it's 3 or 4 lines long, and it has these brackets and parentheses, and it's very hard to understand what it is. And it would be, we don't have enough time to teach you how to name things that complicated. With dienes, a diene is what is considered a difunctional molecule. So you have 2 functional groups in the same molecule. So here's an example of a diene. What has been the underlying principle of all this nomenclature that we've learned? The first thing you do is longest continuous chain of carbons. Very good. So with a diene, it's the longest continuous chain of carbons that contains the 2 double bonds. So with this example, 1, 2, 3, 4, 5, 6, 7, 8. I can fit them all, it's one continuous chain, and that gets both alkenes covered. So this would be octane. But it's not anymore.
Oh, so sorry. You weren't perfect.
No, I know, it's not anymore.
She just
It's octadiene. I think of that octa mom. Wasn't there a mom who had octuplets or something?
Yeah.
Okay. So I have this as my parent name, octadiene. But with that diene ending, I need to have what? Two numbers. Right. So which way am I going to number this octadiene? Left to right. Good. So 1, 2, 3, 4, 5, 6, 7, 8. So I can already tell that organic chemistry is meshing well with you all because you're picking out the numbering schemes right away. You're understanding that this is the way we number it, so you get the lowest numbers on these alkenes. So believe it or not, you have come a long way. It just doesn't feel like it because it's also foreign and new to me. But you're doing very well, so I don't want anybody to lose sight of that. Now, with this diene, the numbers that I'm going to list for my double bonds will be the lowest numbers, so it will be 2, 5, octadiene.
So since the dye is at the end there, you don't have to put the dye.
Yeah. So the format,
Why would they do it? Because you would think that you just add it on melody.
well, you'll.
Maybe it means something more when you get more into it or something.
But it does. There is, I do get a lot of students who will say di, octaene, or, you want to put it that way. But this format does make it easier if you have anything else hanging off of this octadiene. You can imagine having an isopropyl or a methyl. You don't even want to think about it.
Brain cramps.
Yeah, brain. Yeah,
Lab
just
midterm.
stop.
Let's just keep it this simple.
Okay. Yeah, which we do keep it very simple for you with this. But I wanted to show you that the general name for dienes, alka, like alkane, whether it's propa, butadiene, pentadiene, hexadiene. So it's the root with the A plus the diene. This is the generic, very general. And for dienes, the general thing, or a general name would be number, alka, diene. A lot of times students get tripped up on why do we just add ene when it's an alkene? You're adding a vowel to the end, whereas with the dienes you're adding a consonant, so that's why we keep the A and we drop the A with the other one. Okay, so we'll name two of these and then we'll stop. So each one of these molecules represents a lovely lesson about nomenclature. And so we'll go through these. This first one, we've talked about the cycloalkenes. Now we have a cycloalkene. So how many carbons are in this cycloalkene? But within the ring?
A 6.
6. So it would be cyclohexane, but it's cyclohexene. Very good. When you have cycloalkenes, the double bond always gets the lowest number. So this gets, so you can number it this way, 1, 2, 3, or you can number it this way, 1, 2, 3, 4, 5, 6. Yes, you still want your substituent to have the lowest number if possible. The double bond takes priority, and then you have your substituents to think about. So So we're going to number it that way. Since the double bond is always number 1 in a cycloalkene, it would be redundant to say 1 cyclohexene. So it's not stated. So it's just 3-methyl cyclohexene.
Those are connected, not dashed.
Right. It's just all grouped up. Yes, this line right here, so 2 lines right here, that is your double bond. What's that? You're up.
Never given the name of the
It will go both ways. So you can, on the next page, you know, and I always get students who say, like, I like it one way or the other. You know, but we'll have more time to practice this when we meet again. And so we'll stop here for tonight. Take deep breaths. You guys are doing great.